I am Dr. Aslesha from the Department of Aeronautical Engineering. Now in this module of the session, I would like to discuss about the high-speed aerodynamics subject. So, which is a subject which is there at 5th semester aeronautical engineering students. So, in this session, I would like to give the brief introduction about what are the modules are there which we are going to cover in this subject, and what are the prerequisites are required for this particular subject, as well as I would like to discuss about the introduction of the first module 1. Okay, so coming to the module 1, course overview. Coming to the course overview. So what is this course basically serves is about the fundamentals and application of high-speed aerodynamics. So which means the speed of an aircraft or a flight will be of very high speed compared to the low speed. So what all the topics which are going to cover in this particular subject is about, we will study about the compressible flow, how the shock waves has been formed, what is the cause of one-dimensional flow, numerical techniques and experimental methods for the compressible flow. And after learning all these things, it will be able to applicable to design and analyze the typical engineering systems like nozzles, diffusers, intake, shock tubes, and wind tunnels. So this is the entire course view of the high-speed aerodynamics. So before knowing about this particular subject, I would like to ask the students to refer the 4th semester subject, that is aerodynamics, so which is the prerequisite for this particular subject. And apart from the aerodynamics subject, if you have the knowledge of fluid mechanics also, it is very helpful for you to easily to understand about the high-speed aerodynamics. Okay. So what are the course objectives? So what we have seen is of the course overview. Now coming to the course objective, what student will try to learn in this particular subject is, he will be able to understand the basic concept of compressible flow, governing equations of compressible flow, compressibility effect at high speeds and their importance. So, and second course objective is like wave formation, propagation in supersonic flow and the resultant effect of flow properties variation. And the third objective what student will learn is that method of characteristics and compatibility equation and method of solution of isentropic and non-isentropic flows. And at last, student will be able to learn about the various experimental methods to study about the compressible flow regime. So these are the course objectives. So coming to the module 1, what student will be studying in the module 1, what knowledge student will be gaining from that one is about he or she will be studying about the compressible flow, and we will be studying about the basics of the thermodynamics and fluid dynamics, and we will be seeing the governing equations relating the integral form as well as the differential form as well. And we will be studying about the continuum postulates and what is the acoustic speed, what is the Mach number, what are the governing equations which are used for the compressible flows. All these things we will be studying in the introduction to compressible flow. So by the end of this particular module, what student will be able to achieve? So that is like he will be able to utilize the concept of gas dynamics for determining how the compressibility affects the global and local nature of the flow. This is the course outcome. At the end of this module, student will be able to guide. So the Bloom's taxonomy level of this particular module was application level. At the end of this particular module, student will apply the knowledge, whatever he gained from the concepts and whatever he understand, and he will be able to apply for determining the flow characteristics of a compressibility. So in the second module, so in first module, what we have studied is about the basics of the compressible flow and what is a compressible flow, what are the equations are there. So coming to the second module, so at high speeds, what type of flow formation, that is nothing but at high speeds we will be having the shock and expansion waves will be there. So basically students will be learn about how the shock waves will be forming, how the expansion waves will be forming, and what are the governing equations are there, and what is about the supersonic wind tunnel he will be learning, shock tubes, and what are the Prandtl-Meyer expansion flow they will be seeing, and shock expansion methods for flow and airfoil, and introduction to the shock wave boundary layer interaction. One of the important topic which student will be learning, that is introduction to shock wave boundary layer. How this interaction will be happening, with that what effects will be coming inside the flow, and how does it affect the aerodynamic characteristics of a particular flight. Okay. So by the end of this module, the student will be learning how to construct the equations of change in pressure, density and temperature for determining the nature of compression and expansion of the shock wave. levels. So as I told, like they will be studying about the shocks and expansion waves at higher speeds, right? So when a flight is flying at a higher speeds, it means there is a change in the temperature will be there, density will be there, as well as the pressure will be there. So they will be able to construct those particular equation for determining what is the nature of that compression or the expansion waves. So the Bloom's taxonomy level for this particular module is the apply level. So coming to the third module, what student will be learning in this particular module is about the dimensional and one-dimensional quasi-flow equation. So in this one, they will be seeing about the isentropic flow in nozzles, area-Mach relationship, choked flow, under and over expansion nozzle, slipstream line, one-dimensional flow, and flow in a constant area duct with friction and heat transfer, Pannier flow, Rayleigh flow, and flow tables and charts for Pannier and Rayleigh flow. All these things he will be learning in the third module, students. So by the end of the third module, what is the outcome taken by the students? So they will be able to develop the fundamental equation for one-dimensional and the one-dimensional quasi-flow for a compressible ideal gas. So the Bloom's taxonomy level was the apply level, and after this one, what student will be able to gain also, they will be examining the steady isentropic flow with friction and heat transfer for solving the problems in flow through one-dimensional passage. So as the keyword which is here is examine. So it means that particular Bloom's taxonomy level is like student will be having the capacity to analyze the flow. Whatever he has gained the knowledge from that particular module, he will be able to analyze that flow, how the behavior will be there, how it will be there for solving the problems in a one-dimensional passage. So coming to the fourth module, student will be talking about the taught about the application of compressible flow and numerical techniques. So in that one, student will be studying about the small perturbation equation for subsonic, supersonic and transonic hypersonic flow, and experimental characteristics of flow in compressible flow, supersonic airfoils, and area rule. And in that particular numerical methods, which will be of theory of characteristics, determination of characteristic lines, compatibility equation, supersonic nozzle design using method of characteristics. So from theory of characteristics to the design, supersonic nozzle design using method of characteristics, these all will be based on the numerical techniques only he will be learning. So by the end of this module, student will be able to analyze the airflows at subsonic, transonic, supersonic flight condition using the perturbated flow theory assumption for solving the compressible flow over a finite one. So the Bloom's taxonomy level, as I said, it is an analyze level. So coming to the fifth module, that is the last module of this particular high-speed aerodynamics subject is, that is experimental methods in compressible flow. So whatever in the fourth module, the students will be learning about the, first in introduction, you will be learning about the compressible flow, then what is shock waves, expansion waves, how they will be forming at that particular one. Then he will be learning about the one-dimensional and quasi-one-dimensional flow he will be learning. And later he will be learning about the application and the numerical techniques. And at the end, the student will be learning about the experimental methods in compressible flow. To study about how the flow behavior will be there. So for that one, he will be talking about the experimental methods, that is supersonic wind tunnels, subsonic wind tunnels, shock tunnels, free piston shock tunnel, detonation driven shock tunnel, expansion tube characteristic feature, how their operation will be done of these tunnels and what is the performance. And apart from these are the experimental methods, so how it will be there. So to visualize that one, so they will be studying about the flow visualization techniques for the compressible flow as well. So this is for the, at the last module, they will talking about the experimental methods in compressible flow. By the end of this particular module, the students will be having the knowledge of apply the various optical flow visualization technique used for capturing the compressible flow fields. So that is the apply level. So you will be understanding basically what all the flow visualization techniques are there, what types of wind tunnels are there, so that by different flow visualization techniques in the different wind tunnels, how he will be able to capture the compressible flow. That's what at the end of this particular module, student will be able to understand. So this is the consolidated course outcomes for this particular course of high-speed aerodynamics. So in first unit, the student will be able to learn about the basic concept of the gas dynamics for determining how the compressible flow is affecting the global and local nature of the flow. Then construction of equation for changing the pressure, density, temperature for determining the nature of compression and expansion waves. Third one is developing the fundamental equation from one-dimensional and quasi-one-dimensional flow for compressible flow ideal gas. And the fourth course outcome is examining the steady isentropic flow for the friction and the flow with heat transfer for solving the problems in flow through one-dimensional passage. So it will be like examining level Bloom's taxonomy. Fifth outcome is like analyzing the airfoil set subsonic, supersonic and transonic flight using the perturbation flow theory assumption for solving the compressible flow over a finite mean. So that is also analyzed Bloom's taxonomy level. At last, sixth outcome is the apply the various optical flow visualization techniques used for capturing the compressible flow field. So that is the apply level. So these are the 5 modules which we are going to see in this particular high-speed aerodynamics course, and in detail we will study about each and every topic of it will be covered. So coming to the module 1, that is introduction to compressible flow. That module 1 we will be, as I told, we will be studying about the basic concepts of introduction to compressible flow, basic review for the thermodynamics, fluid mechanics, and the conservation equation for the all 3 equations we will be studying: acoustic speed, Mach number, and governing equation for compressible flow we will be studying. So what is the definition of the compressible flow? So compressible flow is defined as a variable density flow, that is contrast with the incompressible flow where density is assumed to be constant throughout. So here the basic definition of the compressible flow means density is varies. So that is nothing but rho. Rho is varies. So whereas in incompressible flow, what we will be telling is that density is constant. But as we see in every flow, if you are considering a fluid is compressible to some greater or less extent. Hence, what we are telling is like density is constant in an incompressible flow. That is entirely a myth. It is not constant. It is bit lesser. We can tell. So if you are considering a flow field, so that particular flow field when it is going at higher speeds, what we will be having, there will be a changes in the pressure change will be there. So due to those pressure changes, there is a change in the density will be there. So when you are talking about the high speed aerodynamics, when the flow field is higher, there is a change in the pressure. With that corresponding, there is a change in the density. So that's why in compressible flow, we are telling there is a change in density is there. So when it comes to the low speed, that is of the very lesser speed, what we will be telling, there is a change in a pressure is there, but with comparison of the change, the density changes is of the very less, very small. So with that one, what we are taking is like the density is constant with respect to the pressure also. Like there is a change in the pressure also, there is still density, the change in the density is the very minute will be there. So for all the liquids, whatever we will be taking under the a certain condition, but the density changes are very small. So that one, the assumption of the constant density can be make it as a reasonable accuracy instead of telling it as a like there is no density. The change in the density will be of the constant which is there. So as you tell, compressible flow is nothing but the density is a variable that requires of the more elaboration when it comes to the compressible flow. So now what we will be doing is like we will be considering a fluid volume, small element, that is a finite volume of V we are considering, and what we are telling, we are exerting the pressure on the sides of the element. So on this particular element, we are exerting the pressure on this one. So by the neighboring fluid of, that is of P. So from the pressure on the sides of an element is occurring by the neighboring fluid which is there, that is with P is the pressure which is. So now what we are telling, assuming the pressure is considered by an infinitesimal element del P. So the pressure whatever is there, so that has been increased with small amount of del P. So the volume of that element with correspondingly compressed by the amount of del P. So whatever the pressure which we are there, so that is with a change in pressure which we are increasing, that is del P. So due to which one, whatever the control volume is there, that will be compressed by del P. So since what we are telling, it is compressing. So since if it is compressing, means what? The volume is getting reduced. So by that time, what we will be taking, the volume is getting reduced, means minus del V we will be considering. So the compressibility of the fluid which has been given as a tau equal to minus 1 by V dV by dV. So this is the compressibility formula, which is nothing but the tau equal to minus 1 by V into dV by dV. So generally bulk modulus is nothing but whatever the change in the pressure to the, so tau, that is nothing, compressibility is nothing but 1 by beta. So this beta is nothing but the, so tau equal to 1 by beta. So this beta is nothing but bulk modulus. Okay. So when you are considering this as a bulk modulus, so beta, so that is like inverse of this one. So this bulk modulus is nothing but how much change in pressure is there with the due to the volume. So dP by change in pressure to the volume fraction, LV by. So that reverse of this particular one, what we will be having. So once you consider, so 1 by dP by dV by V. So this can directly dV by dP into 1 by V. Since we are considering the decrease in the volume, that's why negative sign has been come. So this is nothing but the compressibility form, what we will be getting from this. So that is nothing but what is the compressibility? It is the inverse of the bulk modulus, which is nothing but whatever the change in the pressure with respect to the volume of the change, what we will be having. So del V by V. So that is nothing but the compressibility. So if you are considering the physically, the compressibility is a fractional change in the volume of the fluid element for the change in the pressure. So what we are having here, so del V by del P. So that is nothing but fractional change in the volume of the fluid element per unit change in a pressure. However, this equation, whatever we are considering, it is not sufficiently precise. So for that, so when a gas is compressed, say if a bicycle pump, if you are considering, means it temperature tends to increase. So depending on the amount of heat transfer into or out of the gas through the boundaries of the system. Therefore, if the temperature of the fluid element is held to be the constant due to some heat transfer mechanism, then that is the isothermal compressibility. So what we will be considering now, previous formula is nothing but compressibility is of fractional change in the volume of the fluid element to the unit change in the pressure we are considering. So for this particular one, when your gas is compressed, at that time temperature tend to increase, then depending on the how much of the heat transfer it will be happening to or the outside of the gases within the boundaries of the system. If the temperature whatever is there, if it is held to be constant, then what we will be considering, tau T, that is compressibility with respect to constant, will be given as the isothermal compressibility. It means isothermal compressibility is nothing but temperature of the fluid element is held to be the constant. Right? So next, now that is a condition for the isothermal. Now if no heat is added or taken away from the fluid element, if the compression is adiabatic. If the adiabatic flow means, what does it mean? No heat is added. Or if no other dissipative transport mechanisms such as viscosity and diffusion are the important. If the compression is reversible, then the compression of the fluid element taken isentropically and isentropic compressibility is defined. So that is nothing but, so tau S equal to minus 1 by V dV by dP of S. So where that particular S denotes the entropy constant. So it means that compressibility is also one of the property of the fluid which we will be considering. So now initially what we have seen, what is the tau, generalized tau value we have seen, and with that particular one we can't tell precisely what is the compressibility. So then we have come with the where temperature. So when temperature is constant, isothermal compressibility, what is the formula which we have seen, and then we have seen the isentropic compressibility. So these two we are shown, and we have concluded from that, which told that compressibility is a property of the fluid. So whatever it is, then liquids have very low values of compressibility, whereas the gases will be having the high compressibility effect will be there. So suppose if the fluid element is assumed to be having a unit mass, then we will be considering as a specific volume, and the density we know rho equal to 1 by V. So now what is the formula which we know? So density equal to 1 by V. So we know tau equal to minus 1 by V into dV by dV. So now, from this one, tau is nothing but 1 by rho d rho by dV. So therefore, whenever a fluid experiences a change in the pressure, the corresponding density will also be changing. So from there, what we will be getting is like change in density equal to rho into tau into change in the pressure. So whenever there is a change in a pressure is there in experiences by the fluid, so then there is a change in the density will also be coming. Right? So to that point, I have considered that just fluid within itself is a compressible being a property of the fluid. Now we assume that fluid is in a motion. So if we are taking the fluid is like not in a constant location, it is like continuously moving. So such fluids initiates it maintained by the forces on the fluid, usually created at least accompanied by the changes in the pressure. So high speed flows are generally involving in the large pressure gradient change. So if it is fluidized moving means what it will be happening, there is a change in the pressure. So change in the pressure means if it is moving means in the space it will be moving, right? So pressure gradient dP by dx will be large changes will be coming. So for a given change in del P due to the flow, so equation whatever we have demonstrated, that results the change in density will be for the smaller for the liquids which have the lower values of the tau and larger for the gases. So where we will be having the tau will be of the higher values we will be having. Therefore for the liquids we can tell larger pressure gradients can create the high velocity without much change in the density. So such kind of flows we are assumed to be compressible where density is constant. What we are telling, so dP by dx can create the higher velocities, high velocities. So without changing density. So this kind of flow we will be calling it as a incompressible flow. So that is applicable for liquids, right? So when it comes to the gases, what we will be having, the large values of tau will be there. So there is a stronger change in the pressure gradient will be there. So that will be leading to the density. So what we are telling, d rho equal to rho into tau into dP. So the higher values are there. We will be having the stronger pressure gradient changes elements that corresponding leads to the change in the density as well. So this one we will be having a effect of compressibility will become. So at the same time, such pressure change can create the large velocity changes in the gas. So such flows will be defined as a compressible flow where rho is variable. So for gases less than about velocity, less than about gas velocity, okay, for gas velocity less than about 0.3 of speed of sound, okay, speed of sound. So there will be associated changes are small even though tau is large for the gases. So for gas velocity, gases, and this equation still enough for the dictator to the small del P. So for this reason, what we are telling, low speed flow of gases can be assumed as incompressible. So it means that what we are telling, gas velocity less than 0.3 of speed of sound is considered to be incompressible, right? So this is for today. So we will see with an example. So what will be the compressible flow and what other basic introduction about the review of thermodynamics and fluid mechanics we'll be seeing in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.